Okay, so again, we're looking at rates of change, looking at the average rate of change versus the instantaneous rate of change. Let me just kind of review really quickly what we had looked at last week. So we were looking at slopes of functions, and maybe we had some graph like this, f of x. And if we wanted to find the average rate of change on some interval, let's say AB, so find the average rate of change. Of f of x on the interval AV. So this is not talking about a point. This is talking about an interval of our x value, some value here A, and maybe some value here B. And so if we wanted to find the average rate of change between A and B, basically we're looking at the slope between these 2 points. And so recall, we need the points. Well, when x is A, our y value is f of A. And when x is B, we can find our y value by plugging it back in there and plugging in B wherever you see an x, and that would give you f of B. And so we looked at the change of our y value all over the change in our x value. And so one way to write that is with this triangle. So f of B minus f of A, change of y's all over the change in x. So B minus A. Then we talked about the instantaneous rate of change. So this gives us kind of the average of what the slope is between these 2 points. But we want to find maybe the slope at one particular value. And so far in our mathematical careers, we've been able to only do that on lines. And so now if we want to find the instantaneous rate of change, at x equals A. This is where we were looking at our graph. Maybe this is f of x. And this is some value here, A. This is where we wanted to choose some value that was really close to A. And so let's say we just added a little distance to the left or right of A. Doesn't matter which direction, I usually do to the right, but let's add this or subtract that distance. And we want this distance H to be pretty small. So if I added this distance H to my X value of A, this point right here is A plus H, right? So I would take this line, this A value plus my H value, that would be A plus H. So my Y value there is f of A plus H. And my X value at A, this point right here, is f of A. But we know that we could even get a better estimate of what's going on at A if this distance H is actually smaller. So what we're basically doing is we're saying, okay, let's choose another value H even closer to A. And we're going to get this infinitesimally small. It's basically this H value is going to 0. So H goes to 0. That distance between those 2 points are going to be nothing. And so this is where the definition of limits helps us. And so we can look at this again as a limit as h is going to 0 of our y value. So remember our y value, change in y. So f of a plus h minus f of a all over. Well, normally it's the change in our x. So this is that a plus h minus the other x value, which is a. And so notice the a's cancel in our denominator. And so that's where we had gotten that definition, the instantaneous rate of change at a value x equals a on f of x, if it exists. We'll talk about that in a little bit, is f of a plus h minus f of a all over h. So we then kind of extended this a little further, and we talked about finding the equation of a line. And so when it was between 2 points and we were looking at the average rate of change on some interval, we called that line was the secant line. So the line that joins it is called the secant line. And then we looked at the slope at that one particular value, that instantaneous rate of change. And it's the line that goes through this point and has the same slope. And so if I were to look at that and I drew a line that goes through this point with the same slope, it would look something like this at that point. And that line that went through that point with the same slope, we called the tangent line. Okay, so that I believe is where we left off last week. And so now we're just basically pulling what we just learned and defining what the derivative is. So you basically been finding the derivative. The derivative has a couple of different ways that we can say it. We can say we want to find the derivative of a function at a particular point, or meaning the same thing, we want to find the instantaneous rate of change at some point. Or the derivative is also known as the slope of that tangent line. So let's define it. Okay, so the derivative. So the derivative of a function is f at x defined as, so the derivative, oops, of a function f at x is defined as the following. So there's different notation to describe that you're talking about the derivative and not the function f. And so if we were talking about the derivative, one way, and this is normally write it this way, is f, and then it kind of looks like an exponent. It's like a prime here. We call it prime or a dash, parentheses x. So this is just saying the derivative of our function f of x at x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. We have to provided this limit exists. So this actually, what I just gave you, gives the derivative anywhere, any x value you choose on our function. So this is a function. The derivative is a function. And so if we wanted to find what the instantaneous rate of change or the derivative at some value x equals a, so if we want the derivative, x equals a on f of x, we would denote it as f prime parentheses a. And just like we were just doing before, this is equal to the limit as h goes to 0. But instead of putting in an x here, we're putting in a. So this is f of a plus h minus f of a all over h. Again, we have to provide it exists. Okay, so again, the derivative has several different interpretations. Two that we have discussed. The function f prime of x, let me just read this, represents the instantaneous rate of change, y equals f of x with respect to x. This instantaneous rate of change could be interpreted with marginal costs, marginal revenue, or marginal profit. If the original function represented either cost, revenue, or profit. It could represent our velocity if the original function was our position function. So from now on, we're going to use rate of change to mean instantaneous rate of change. So that's a key right there. So later on, when we have a word problem and it says find the rate of change at the cost of x equals 100, then you are going to look at the derivative. Okay, the other interpretation that we got was, excuse me, the function f prime of x represents the slope of the graph of f of x at any point of x. So if the derivative is evaluated at x equals a, then that represents the slope on the curve at x equals a, and or the slope on the tangent line at that point. Okay, so we've been already working with it. Now we're just giving it a new name, the derivative. So let's look at some examples. For some reason, my mouse doesn't like being. So we had a great question was, is there a difference? Can we just, between using x plus h and a plus h, can we just use a plus h? And so really what we're doing when we have it where we don't have a in there, we have that x value. This is giving us the derivative anywhere on our graph f of x, where if we were given our value x equals a, so wanting to find the derivative at x equals a, we might use this formula. Actually, it's probably better we use this. And once we use this formula, once we have the derivative, then we can go back in and plug in a wherever we see an x in that derivative function. And so in a way, this first formula is easier because if it wants us to find the instantaneous rate of change, or another way to say it, a derivative at more than one x value, it would be easier to have this function so that we can go in and just go in and plug in that number for x in each case. So let's look at some examples using that. Any other questions?